Hey everyone, hope you guys are doing well after your first day of classes. I'm sure it was a little overwhelming, but just know that it only gets harder from here. All right, so we're gonna keep trucking along here. So this video is gonna just mainly talk about 6.2. All right. We started 6.1 in class today. You know, I didn't really do that much, but we started 6.1. We talked about top minus bottom. I posed a question. I hope you guys are ready to talk about it a little bit during our next lecture. But I posed the question of, does this always work? And I really hope you guys spend a minute or two to kind of think about that and come up with something. All right. Hopefully we can talk about it a little bit during next class. But 6.1, the remainder of 6.1 and along with 6.3, China's actually just going to go over that with you guys during recitation on Tuesday, June 30th. Okay? So 6.1 and 6.3, she'll take care of it. And then this video is just mainly going to focus on 6.2. Okay? Well, what is 6.2? It is volumes with known cross section. So I would say watch this video before the recitation if you can, but if not, it's fine. Just because 6.3 talks about volumes with the where the cross sections are circles. You guys may know it as disc and washer. So yeah, but 6.2 kind of like it's the more, I would say, generic of finding volume. It's basically when your cross sections aren't circles, they could just be whatever. I mean, they could be circles, but they can basically be whatever they want, right? To kind of like paint a picture here. Imagine I had a triangle, right? And I had an infinite amount of like these triangles, right? And like I just started like stacking them on top of each other an infinite amount of times, right? Oops, an infinite amount of times, right? What would I end up getting? Like what would start happening, right? Well, you would see that you end up getting like this. You'd end up getting this like triangular like prism, right? That starts to generate as you add on more and more height to your three-dimensional figure, right? So that's essentially what we're doing here, right? Where I tell you what the cross sections are, right? What these little pieces that we're adding are, and you have to figure out, well, like what is how much is of the volume is going to be generated over what bounds and yada yada yada. All right. So there are two. Let's say two. Let's say two big examples I want to go through here. So let's start with an easy one. Okay. So let's start with this guy right here. This figure you guys should all know is your handy dandy cylinder, right? And you learned that the volume of a cylinder is pi r squared h, right? But do you know why it's pi r squared h? Do you know where that comes from? Do you know why it is the way it is? Well, we can actually prove it real quick using calculus, all right? Believe it or not. So what are we going to do here, right? I'm actually going to just fix this cylinder on the coordinate plane. I'm going to say that it's centered and that it's going upwards, right? So what does this mean? Well, we know that actually. I made a boo boo. Let me do it the other way. Let me fix it the other way because I think it's easier that way. Because you guys are used to x's and stuff. So let's fix it this way. Okay, where the cylinder is kind of fixed at the origin, and it's the way it is in the picture, right? I'm sorry if my pictures aren't good. I'm not the greatest artiste. I'm gifted in other ways, okay? So what are we going to do? The way we think about this is, well, if I were to look at one of the cross sections, right? If I were to look at one of the cross sections, I notice that there are thin slices of, I don't know why I was going to say cucumber. There's thin slices of circles, right? With really, really thin heights, right? If I were to draw it out, it would look like this. This is like one of the slices. Like I said, once again, it's not perfect. I'm sorry. All right. So, and we know some things about these thin slices of not cucumber, circles, right? We know that there's going to be a radial length. Okay, it's going to be some r value, right? And in fact, this R value is fixed. What that means is it doesn't change, right? The radial length of a cylinder, it'll never change no matter where you are in height-wise. So if we kind of put it all together here, I can say, well, I want to add up a bunch of a bunch of circles, right, that are stacked on top of each other, and then take my cross section, take the area. This is the area of the cross section from this value to this value, right? From 0 to that question mark value. And if it makes sense, that question mark value should be the height of the cylinder, right? So from 0 to h. I hope that makes sense, right? Our area function in this case, it's actually going to be pi r squared because, well, the area in this case is a circle. And we know that pi r squared is the area of a circle. So what are we essentially doing? From 0 to h, pi r squared dx, right? And you're looking at this integrand, okay? You're looking at this piece, and you're like, wait, what is that? There's no x's in there. I don't know how to integrate, right? Think about it. Stop and think about it for a second. R, we just said, was fixed. This is fixed, so this is a constant. Pi is actually also a constant. And what do we know about constants in the integrand? We can just take them out. So what does this become? Pi r squared, I took that out. Integral from 0 to h of 1 dx. And from here, you guys should know what to do, right? I can integrate this. Since our cylinder is, fixed with respect to x, I'm integrating with respect to x. Please don't forget that dx. It's so very important. This becomes pi r squared times the integral of 1 dx, which ends up being x from 0 to h, right? Hopefully you guys know this notation. This ends up being pi r squared times, well, if I plug in upper minus lower, right, this should not be new for you guys. You get h minus 0, and oh my gosh, I get pi r squared h. Oh man, that's so cool. That's where it comes from. I didn't know that. Yes, you can use calc to prove this kind of stuff, and it's really, really interesting. It's a lot of fun to do, all right? Yeah, that is the first example. I should have said that. That was the easy one, all right? I'm going to do a harder one, one that is still familiar to you guys. I'll call this example 2. And yeah, you have to be able to think this way for these types of problems. In fact, wink, wink, I'm just saying this here. Look at the examples in this section, okay? Look at the examples in this section. Wink, 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 cough, it's going to be on the midterm, okay? All right, so for this second example, we're going to look at a sphere, right? Oh, I should have written that smaller. Whoops, let me just retry that here. Volume of a sphere, right? We know that it is 4/3 pi r cubed, right? So why don't we prove it? Why don't we prove it like we just proved the cylinder? So here we go. Here's my coordinate plane. We're going to be spilling out into the z-axis, which is the third dimension here, if that makes sense, right? Oh, God, that is a terrible circle. Let's try it again. Oh, my gosh, that's still terrible. Third time's the charm. Ew, I suck at this. All right, whatever. Okay, so pretend that's a sphere, right? I did my best. And we're going to approach this problem like we approached the cylinder problem, okay? We're going to take a cross-section. We are going to define some things. We're going to look for any constants and then use integration to add up all of the cross-sections, okay? So, so if you haven't picked up on it yet, this is like the generic formula to find the volume of something. You just add up the cross-sections an infinite amount of times. So here we go. Let's look at the sphere, this perfectly drawn sphere, and let's take a cross-section. What is a cross-section going to look like? Well, I'm going to zoom in a little bit here. If I look at a cross-section here, I see another circle, right? I see it's going to be another circular piece, okay? Now, we have to kind of define some things here because there are actually some variables going on here that you may not see. All right. So first and foremost, let's define the big radius. So this is big R is going to be the radius of the sphere. right? So from the center out to any point on the circle, the sphere, that's going to have a length of capital R. So in fact, I can find our bounds, right? This is going to be negative R, and this is going to be positive R, because that's how big the sphere is, right? If it's centered at the origin. So we have big R, which means radius of the sphere, and we actually can just say that this is going to be a constant. That's going to be important very soon. All right. Now, there is another radius going on here. All right. It's important to make sure you know which is which, and I'm going to define it as little r. And little r is going to be the radius of your cross section. Now, that little r is going to change, right? That little r is not always going to stay this length, right? It depends. Like if it's over here, right, little r is going to be like shorter, as you get closer to big R. Or it's going to get bigger as you go to the middle, and so on and so forth. So that's actually going to be something that's dependent on where you are on the sphere. So the last variable that we're going to need is x here, and x is just your friendly, x, right? This is going to be in between r and negative r, if that makes sense, right? X is the x value on the x-axis, right? And these values are only going to live in between negative r and r. So we kind of just can come up with a domain for it real quick, right? So I think we have everything we need. We just need to now ask the question here. What is my a of x? What is the area function that I'm going to need to integrate from, it looks like from negative r to r. So we can kind of fill in some holes real quick, right? So volume of the sphere is going to be the integral from negative r to r. And we need a function, right? This is a function in terms of x, right? Has to be a function in terms of x. Well, what can we do here? We can come up with a relationship that ties together big R, little r, and x, right? If we can tie them all together and come up with some sort of relationship, we can use that to figure out our area function. So in this case, right, I'm going to see I'm going to look at my sphere and see if I can kind of pick out anything, right? I see, if I'm just looking at this cross section here, I see that this big R right here, this radial length, capital R, and then I see the little r here, right, which is the radius of the cross section, and I see, oh my gosh, that's an x, and we actually end up having a right triangle. Oh my gosh, Pythagorean's theorem strikes again, right? If I use these three terms now, I can come up with a relationship. I see that x squared plus little r squared is going to equal capital R squared, right? So if that's the case, I can create a function. Create a function in terms of x. Okay, I'm going to create a function in terms of x. Well, what does in terms of x mean? It means everything with an x in it, right? So I'm going to subtract r squared from both sides, right? And get, I'm sorry, I screwed that up, my bad. I'm going to subtract x squared from both sides. And essentially what I'm doing here is solving for little r. Why? Because go back to this. What is our area function? Our area function is pi r squared, and we need that little r. Actually, we need r squared, which we just found right here, right? So hopefully this is making some sense, right? Our area function is pi. I'm going to put that on the outside. R squared dx, right? Well, I can replace the r squared now with our substitution here. So it's going to be capital R squared minus x squared. Now we have a function in terms of x, and well, big R is a constant, remember? And now we can integrate this. Before we couldn't, because if it had like little r's in it, that would be like a different variable that we're integrating with respect to, and it would have just cause more chaos, right? So this is it. We have our setup here. All we have to do now is just integrate and hope that our answer looks familiar, right? So here we go. Let's try this. Pi, excuse me, pi times the integral of r squared minus x squared. So the integral of r, capital R squared, well, that's just capital R squared x, right? Remember, you think of r squared as a constant, right? So minus x cubed over 3, right? Because that is the integral of x squared, and we're taking this from negative r to r. I know the capital R's might be throwing some of you off, but remember, they're all just constants. There's some value that the sphere is going to hold, right? Because every sphere has the same radius. Okay. All right. So from here, we like this part, right? We can just plug in the upper bound. In this case, the upper bound is r, so this becomes r cubed minus 3. And then, so let me just highlight that real quick. So this is the upper bound that we plugged in, and then minus the lower bound that we plug in. So, and the lower bound is a negative r, so watch out. This is going to be negative r cubed plus r cubed over 3. Right, this is the lower bound. And I really hope you guys are taking notes on this in your notebook. I should have said that in the beginning, right? Oh, well. This becomes, just do some algebra here, right? These end up doubling on what happened in the upper bound, right? So this turns this into a positive r cubed. So there's 2r cubes, and then minus 2r cubed over 3. This is the same thing as 6r cubed over 3 minus 2r cubed over 3. And holy guacamole, I see it, 4/3 pi r cubed. Does that look familiar? It sure does. Where is it? Oh, it sure does, right? Look, there it is. So what did we just do? We just used integration to prove the volume formula, knowing the cross sections of the sphere. Whew, you guys can should probably take a break here, all right? Maybe like scrub back a little bit, go through the problem again if you need to. But I know it was a lot, but definitely know how to do a problem like this, okay? And I said it before, I'm not gonna write it down. Wink, wink. Check out the other examples in that section. We're in section 6.2. All right, check out the other examples in that section. Okay, I just looked at the clock. Holy moly, 18 minutes. This is crazy. I will do my best to shorten these videos. I apologize. It's just because there's a lot I had to go over. All right. I'll do my best to chunk these videos a little bit better in the future. All right. But that's it. That's pretty much all I wanted to cover. 6.2. Knowing the cross sections and stuff, you should be able to do some. I'll help trying to pick out the problems for the homework in this section. But yeah, at this point, you guys should be ready for problems like these. All right. Once again, if you're not on the GroupMe, please get on the GroupMe. If you need anything, email me. And yeah, I guess I'll see you guys on Wednesday.